Hey guys, welcome back to another lecture video for Chem 104. In today's video, we are going to be talking about addition reactions, specifically for alkenes. And so there are two addition reactions that we're going to discuss in this chapter, and we're going to see it again in the next chapter. And so when we're talking about addition reactions, I want you guys to think about two reactants in which one reactant is being completely absorbed by the other. And so the product that you would get is the combination of those two reactants. And so we're going to go ahead and take a look at this through alkenes, so reactions of alkenes. And so the main idea for an addition reaction with an alkene is that one bond of the double bond, so one of the bonds that creates that double bond, is broken to form two new single bonds, producing a new product. And so to visualize that statement, we're going to go ahead and look at this image at the bottom. So here we have an alkene on the left-hand side. And what's going to happen is that this bond, or the other one, it doesn't really matter, it's going to break. And whenever you guys break a bond, I'll just go ahead and redraw it up here. So you have C. When you guys break a bond, remember that a bond is composed of two electrons. And so when you break a bond, those two electrons are going to go back to its original owner, if you will. And so if that same scenario happened for the other reactant, and we're not going to go through the detailed mechanism of this addition reaction, it's out of the scope for Chem 104, and it's something to be discussed in the full year of organic chemistry. And so I'm just going to keep my explanation as simple as possible, even though maybe the mechanism is not correct. And so once again, the idea is to break a bond. And so to break a bond, the electron goes back to its original owner. Okay? And so what once that happens, you get an electron, another electron back onto its original owner. And to form a new bond, it requires two electrons. And so you can imagine that this substance, is then going to form a new bond by sharing the electrons that it had gained once those single bonds were broken. And the resulting substance is simply the addition of the two reactants. Okay? And so hopefully, even though the mechanism is incorrect, I'm just trying to keep it as simple as possible. Hopefully by going through that motion, you guys understand how one reactant is added to another. And this is only made possible because of that extra bond between the two carbons. So if you guys have a single bond between two carbons, that would not be possible, because then you would break the actual carbon chain into two pieces, creating two new products. But here we're only creating one product. All right, and so the idea of addition reactions can be applied using different reagents and different reactants as well. And so the idea is that we have one of the double bond, broken such that those electrons are free to be shared to another substance. So there are two reactions that we're going to be focusing on. We are going to be focusing on hydrogenation, and we're going to focus on hydration. And so we're not going to focus on halogenation or hydrohalogenation for Chem 104, but that's something that can be observed. That's something that is observed and taught in the full year of organic chemistry. And so we're going to go ahead and start with hydrogenation. So hydrogenation is the addition of a hydrogen, diatomic hydrogen, to an alkene. Okay, and so if you guys look at its name, hydro, it might feel like it's referring to water, but if you kind of extend this line, hydrogenation, okay, so you're adding hydrogen, and remember hydrogen is naturally diatomic, to an alkene. Okay? And so once again, if you guys can imagine that these two bonds, if you guys can imagine that one of these two bonds is broken such that the electrons go back to its original owner, so to speak. And if that scenario holds true for hydrogen, so let's just say that the electron goes back so that we get hydrogen separated from each other. These two electrons can now be shared, forming our product. Okay. And so this reaction doesn't happen spontaneously. This reaction needs a metal catalyst. And so one of the requirements for hydrogenation is the hydrogen gas is obviously one of the requirements, and an alkene. But the catalyst, the metal catalyst that's required, should either be palladium, nickel, or platinum. And the product that you guys get from a hydrogenation is always an alkane. So you guys are going from a double bond to a single bond. Okay. So you're going from something that's unsaturated with hydrogens to something that is saturated, that's more saturated with hydrogens. And that makes sense because you're adding hydrogen to carbon, so you're making it more saturated with hydrogens. Okay, so that's the basic premise of hydrogenation. And so overall, you would get a chemical reaction. You'd write a chemical reaction similar to this. Now, another way that this can be written is if you have, for example, that ethylene, and you can simply have the second reactant on top of the arrow. And at the very bottom of the arrow is going to be your metal catalyst. And what you would get is still ethane. Okay. Now, how would this look like in terms of a skeletal structure? Well, if you have ethylene, you just have a double bond and two carbons. And then you guys are going to put in H2 and palladium. And what you get is an alkane. Okay. And so this would be the skeletal, this would be what you guys would draw as a skeletal structure if it was ethylene that you guys are starting off with and producing ethane. Okay. All right. And so the next addition reaction that we're going to discuss is hydration. And so hydration, now you guys are thinking of water, okay, to hydrate yourself. And so hydration is the addition of a water molecule to an alkene. And so if you are looking at this specific diagram, you're starting off with a double bond. and you're still producing a single bond after the reaction occurred. Now, instead of H2 as your reactant, it is water as your second reactant. And so H2SO4 is going to serve as our catalyst. And so it's going to speed up the rate of the reaction so that the product can be formed. And so this catalyst kind of acts like that palladium that I mentioned earlier. However, it's specific to a hydration reaction. Okay. So try not to mix those two up. If you guys have palladium, nickel, or platinum with H2 gas, that's going to be a hydrogenation in which the product is simply going to be an alkane. And so here, for hydration, since your catalyst is H2SO4 and your reactant is H2O, the product is still going to be an alkane, but you actually produce a functional group that we're going to discuss in a future lecture, which is an alcohol, an OH group. Okay. And so it turns out that one of these hydrogens is going to go to one of these carbons, and one of these, and the remaining piece, the OH, is going to go to the second carbon. That's the theory behind it. But this is just a generic alkene. There are some other underlying scenarios that we're going to discuss in just a second that will influence where the hydrogen is going to be placed and where the hydroxyl group or the alcohol group is going to be placed on the alkene. And so unlike your hydrogenation reaction, your hydration reaction forms a product, forms an alcohol in your product. And so that alcohol is going to be that OH. So don't think about the alcohol that you consume. In terms of organic chemistry, the alcohol is a functional group that we're going to discuss in future lecture videos. But for now, just think about OH. Okay, OH is your alcohol functional group. And we'll also understand why alcohol is called alcohol. And like I'm talking about beverage in this scenario. And so, why is alcohol called alcohol, right? What part of it is called alcohol? And we'll figure that out in upcoming lecture videos. Okay. All right. So a little bit earlier, I mentioned that your OH group and your hydrogen is going to be added to the carbons that contains the double bond. However, not all alkyl groups or alkenes are built similar to each other. In other words, there are some alkenes in which it is asymmetric. And so if it is asymmetric, your alcohol goes to the carbon that has the least number of hydrogens attached to it. So let's look at an example. And so here we have our carbon, our double bonded carbon, but you notice that this hydrogen is present. Also, you'll see two other hydrogens that's present on the right-hand side. And so what you also see is a CH3 that's present on the left-hand side, but on the right-hand side, so if I were to cut across, if I were to create a plane along the vertical, there is no CH3s on the right-hand side. And so you would say that this is an asymmetric. alkene. And so if you have an asymmetric alkene, that's going to tell you that the addition of the OH group in water and the hydrogen in water is going to be placed in a certain way, a certain fashion. And so your alcohol is going to go to the carbon that has the least number of hydrogens attached to it. And so if you look at the carbon on the left-hand side of that dotted line, there's only one hydrogen here. And if you look at the carbon on the right that has the right of the dotted line, it has two hydrogens here. And so since this carbon only has one hydrogen, this is the least. And so the OH is going to attach itself onto the carbon on the left and not the carbon on the right. The hydrogen will attach to the carbon on the right for this example. Okay. So it's not so much left or right. It just happens to be left or right in this case. What you want to focus on is the number of hydrogens each of the carbon has on either side of that double bond. And I'm talking about like the direct attachment of the hydrogens, not like the CH3. So don't count these hydrogens. Okay, you're only looking at the hydrogens that are directly attached to the carbons that make up, that shares that double bond. And so the final product that you're going to get is the alcohol that's on the carbon that has the least number of hydrogens. And that hydrogen from water is going to go to the side that has the most hydrogens. So hydrogens with hydrogens. Okay. So think about it like a party, right? You go to a party where you're familiar with people, whether they're friends or your family. There's like a comfort in going to a party where you know everyone. And so hydrogen, wants to go to the party, so to speak, that has other hydrogens in it. And so since the carbon on the right-hand side has more hydrogens, then the hydrogen that's going to be added from that water molecule is going to go to it. Where your OH is just kind of like that rebel, like, oh, I'm a free spirit, I get along with everyone, and everyone loves me, so I'm just going to go to a party where I don't really know anyone and make friends. All right, horrible analogy. So we're going to go ahead and get some practice predicting the products. And so my expectation for you is to be able to predict the products given the reactant and given the reagent. And so let's go ahead and go over a few examples. And then we're going to go ahead and use the same examples for hydration. So right now we're going to go through examples for hydrogenation. So hydrogenation. All right, so for hydrogenation to occur, you need a couple things. You need H2 gas and you need palladium. You can also replace palladium with nickel or platinum. Okay. So all three of these, if you see them at the bottom of your arrow or somewhere on your arrow, then it's implying that a hydrogenation reaction is going to occur. And so what's going to happen is that for every single double bond that you see on this molecule, your hydrogens are going to attach to it. And so you can imagine that you have lots of H2 gas. And so you have like an H2 gas here, you have an H2 gas here, and you have an H2 gas here. So we're going to assume that we have always excess of this hydrogen gas. And so since we have 3 double bonds, all 3 of those double bonds are going to be hydrogenated. They're going to react in the presence of hydrogen gas and one of these metal catalysts, palladium, nickel, or platinum. And so if you guys recall from earlier, once you add those hydrogens, then you go from a compound that's unsaturated to a compound that's saturated. Okay? And so if you guys want to do this methodically, even though this is not correct, you guys can go ahead and create like dots, right? And so that's going to demonstrate where those hydrogens are going to be attached to. And so the final product is going to simply be this molecule. Okay. And I'm going to go ahead and maybe I should do hydrogen in blue. And so all of these hydrogens are in blue. So when you perform an addition reaction, hydrogenation, you guys are going to have a hydrogen that's attached to where all of those double bonds were. So you have these 2 hydrogens attaching and replacing that double bond, okay? And it becomes a single bond. And you have another hydrogen that's going to be added into this section. And once you add hydrogen into that section, that double bond goes away. And so the reason why it goes away is because the electrons, right? So let's think about this. The electrons that creates that double bond gets destroyed, it goes back to its original owner. Remember, there's 2 electrons per bond, and so 1 electron goes to one of the carbons, and the other electron goes to the other. And the same thing is going to occur for hydrogen. That singular bond between hydrogen, that's going to be broken, and the electrons that make up that covalent bond between the 2 hydrogens are going to be broken, and it's going to be reformed by sharing its electrons to that of the carbons. And so you can imagine that those 2 hydrogens are now latching on to those 2 carbons at the bottom of this molecule. And so this is the product that we would get. So the last thing that happens is that this 3rd double bond is going to react again with hydrogen gas. And it's going to go ahead and produce this substance. And so long story short, for hydrogenation, all double bonds, they become single bonds. So all you're doing is you're redrawing the same structure, but without any double bonds. Now, if you guys recall, if you guys did this on your exam, that's fine, I'll accept it. But if you guys recall, if you guys are doing the skeletons, if you guys are writing the skeletal structure, if you're depicting organic compounds using the skeletal structure, you don't really add or include any hydrogens. And so this is a typical way for you to represent the product of a hydrogenation reaction. Simply all double bonds are erased, and whatever's not shown, it's implied that a hydrogen is added or is now there. Okay. Now, if you want to show your work and just show where all those hydrogens are located, from the addition reaction, you can very well do so. Just make sure that you guys are adding in the correct number of hydrogens. So let's go ahead and look at this next example. In this example, here we see a cyclic alkene. I kind of skipped on how to name cyclic alkenes. That's fine. Lots to cover this semester. And so here we have H2, and I'll just put a nickel this time. So remember, nickel is one of those metallic elements that can catalyze this reaction. And so if we have two double bonds, this is where your hydrogens are going to add itself onto this molecule, replacing the double bond with that of a hydrogen. So you're adding hydrogens to it. And so the product of this reaction, if I were to ask you guys on an exam, I should just copy and paste that. It would simply be this. Okay. Now, if you want to show your work by showing all the hydrogens, you can very well do so. So those hydrogens are going to be attached to this part of the molecule of where that double bond was. And you'll also have a hydrogen in this part of the molecule where that double bond was. And so it's not necessary for you to show your hydrogens, but if you want to show your hydrogens to depict where the hydrogens were added to, you can very well do so. Okay. And so if I were to take those hydrogens away, then you simply get an organic compound that looks like this. And so that would be the product of this reaction. And so let's go ahead and look at this, this reactant. So if we have hydrogen gas, let's just say platinum this time instead of nickel or palladium, what would my product be? Okay. And so I'll give you guys just a little bit of time. Feel free to pause this video to kind of draw the product or predict the product. Okay. All right. And so since hydrogenation adds hydrogen to the double bonds, and since hydrogens are typically not shown in a skeletal structure, we're simply going to erase our double bonds, and that would be our final answer. Now, if you want to show the actual addition of the hydrogen, you can. Since that double bond was present, over here we have hydrogen, and we'll have another hydrogen added to this carbon. And since there's a double bond at the tail end of this organic compound, we can go ahead and show that hydrogen is added at these two carbon positions. Okay. All right, so one last example. And so once again, if we're doing a hydrogenation reaction, we know that we are going to use hydrogen gas. And then let's go ahead and use palladium once again. And so if you guys are trying to predict the product for this reaction, since there's a double bond between these two carbons, that's where those hydrogens are going to be placed. And so if you guys are looking at some of these molecules, they're asymmetrical, right? So if you look, if you cut this in half, it's asymmetrical. If you guys cut this in half, it's asymmetrical. Same thing here, well, this one's symmetrical. But since what we're adding is the same item, hydrogen and hydrogen, we don't really have to pay attention and what carbon that hydrogen is going to attach to which carbon. It becomes irrelevant because we're attaching the same substance onto the carbons that contain the double bond. Okay. So we don't have to think about asymmetry or symmetry for hydrogenation. And so this is going to be our final answer if we wanted to describe the product without the hydrogens being shown. Okay. Oh, guess not. I guess there's one more. And so if I do this with nickel, the product that you guys are going to get is simply this. If you want to show where the hydrogens are added, they were added between these two carbons. Okay. Now, if you don't want to show them, you don't have to, because the skeletal structure ignores hydrogens. All right, so what we're going to do now is we're going to repeat the same process, but this time we're going to do it for hydration. And so if you guys recall, hydration requires water and sulfuric acid. And sulfuric acid will be our catalyst. Okay, so if we have excess water, and this reaction was done in a very acidic solution, so H2SO4 is a strong acid, so the pH of the solution is very acidic. Now if you have excess water and you're going to try to perform a addition reaction to this alkene, and therefore the process is known as hydration, what's going to happen is that this water that you're adding so I'm representing water as H-OH. The hydrogen is going to go to the side of the double bond that has the most number of hydrogens, right? Think about it like a party. And the hydroxyl group, it's that, friendly person that just gets along with everyone. So it's going to go to the side that has the least, it's going to go to the carbon that has the least number of hydrogens between that double bond. And so let's go ahead and look at this double bond right here. And what I'm going to do is I'm going to show my hydrogens, my original number of hydrogens. And so here I have 1, 2, 3 bonds. So that means I need one more bond to make sure that that carbon has the full octet. And so that bond is going to be linked to a hydrogen. So there's one hydrogen that's not typically shown. Here there are 2 hydrogens that are not shown. And so this hydrogen, the hydrogen in blue, is going to go to the side. So first of all, this is going to break. Somewhere in the reaction, that bond is going to disappear, and the electrons goes back to its original owner. Same thing here. The bond is going to break. The electrons are going to go back to its original owner. And so this hydrogen, it's a free agent, and it's now able to go to the side that doesn't have, or that has a lot more hydrogens. And this hydroxyl group, this OH, is also going to be a free agent, and it's going to go to the side that has the least number of hydrogens. Okay. And so if we're going to draw this structure, I'm just drawing one part of it at this point. So I'll go ahead and draw those double bonds. And so basically, the OH is going to be added here, and that hydrogen is going to be added here. And the pink represents the original hydrogens that was present before water was added. Okay. And so if you look on the opposite side, here we can go ahead and add in those hydrogens that are typically not shown. And you're adding in you're adding hydrogens based on the maximum number of covalent bonds the carbon can form. So if there's only so if a carbon only has 2 covalent bonds, then it's going to have 2 invisible hydrogens. And so if we're trying to add H2O, so I'll go ahead and add another water molecule, okay, in green. So I'll go ahead and erase this bond because at some point in the reaction that bond disappears. So hydrogen in OH is now a free agent. Where do you think this hydrogen, the green hydrogen, is going to go? And so it is going to attach to the carbon that has more hydrogens bonded to it. And then this hydroxyl group is going to go to the carbon between those 2 double bonds that doesn't have a lot of hydrogens to it. And so the resulting structure that we get, and remember that double bond disappears because the electrons in that double bond is now shared between the new hydrogen and the new OH group that it's attached to. Okay. And so let's go ahead and take a look at this double bond. And so for this double bond, we have to look at the number of hydrogens it originally has before we make a decision in which place the hydrogen and the OH group is going to attach to. Oops. And so since each of those carbons on either end of the double bond has 3 covalent bonds already present, it naturally only has 1 hydrogen. And so once the hydration reaction occurs, that double bond is gone, forming a single bond. Now, if you look on either end of these carbons, notice that they both have 1 hydrogen. So this tells us that there's really no preference for which side the OH or the hydrogen is going to go to. So at this point, you can go ahead and you guys can go ahead and add it wherever you feel like. Okay. And so if you added it in this position, that's fine. If you guys added it such that the OH is on the left and that hydrogen is on the right, that's also okay. Okay. And the reason why is because we have the same number of hydrogens. So there's no preference for the hydrogen and hydroxyl group. It has no preference for where it's going to attach to. And so if I were to clean up my work, and just showcase the final outcome, I would have a hydroxyl here, a hydroxyl here, and a hydroxyl here. Or you guys can have your hydroxyl here. And so the reason why it doesn't matter at this point in time is because both of these substances are symmetrical. And so if I were to flip this molecule, if I were to rotate it 180, I would get exactly the same as this, and vice versa. Okay. So they're technically the same molecule. They're just rotated. All you have to do is just rotate them. Okay. And I'll go ahead and describe that angle as 180-degree rotation. All right. So let's go ahead and look at the next example. I'm going to start picking up. I'm going to skip some of my steps here. And so I still have that H2O and H2SO4. And so if I see H2O and H2SO4, this is a hydration reaction. And so in my hydration reaction, anywhere that I see double bonds, I'm going to replace that double bond with an OH and a hydrogen, such that the OH goes to the side that has the least number of hydrogens. And so I'm going to go ahead and write all of my hydrogens that I originally have before the reaction occurs. And so I have 2 hydrogens here on this carbon because that carbon only has 2 covalent bonds and it needs 4. This carbon right here actually does not have any hydrogens because there's already 4 bonds. So hopefully you guys can count it. 1, 2, 3, 4. 1, 2, 3, 4. Okay. And so there are no hydrogens at that specific carbon. And here there are 1, 2, 3, 4. 1, 2, 3, 4. Okay. So hopefully you guys understand. Okay. So looking at this double bond, the hydrogen in water is going to attach on the right side, leaving the hydroxyl group to attach on the left side. And so if we're trying to draw this structure, I'll just copy and paste. It's probably better. Okay. All right, so if I'm trying to attach the hydrogen and the hydroxyl group onto this carbon and this carbon, the hydrogen is going to go to the carbon on the right. And so when that reaction occurs, you need to erase your double bond and you need to add that hydrogen from water. And the hydroxyl group is just going to be on the opposite side of where that carbon was, right? So this is where the double bond was located. The left side of that carbon has the least number of hydrogens. And so that's where you're going to attach the hydroxyl group. Now for this substance that's on the right, or on the left, sorry, the double bond that's on the left, since there was one hydrogen, it doesn't really matter where the hydroxyl goes and where the hydrogen goes. Actually, there's going to be 2 products this time because this molecule is not symmetrical. And so what you're going to do is you're going to erase that double bond. And for the first possible answer, I'm going to put the hydrogen up and the OH down since they both have 1 hydrogen and 1 hydrogen. And so I'm going to go ahead and duplicate this to draw a second possible product, such that your hydrogen is at the bottom and your OH is at the top. And so these two are very distinct molecules. And if I were to erase all of the hydrogens and just keep the hetero atoms, notice that if you were to flip the molecule at the bottom to try to align it with the top, it will not align. Okay. Or you don't even need to flip it. I mean, you can like literally drag this over, right? And if I drag it over, notice that your OHs, yeah, they'll match, but your hydrogens and your OH down at the bottom, I can't like show you right now because I'm holding this molecule in place. But if you were to look, the hydrogens, the OH at the bottom, they do not match. Okay. And so therefore, you'll have two different answers. Okay. All right. And so if you draw both, that's cool. If you guys are only able to draw one, that's fine too, as long as you guys draw at least one correct structure. So looking at this example, we're going to do another hydration reaction. So here we have H2O and H2SO4. And we're going to take this H2O and we are going to decompose it into H and OH. And we're always going to assume that we have excess, right? You imagine your reaction, that's aqueous, you have a whole bunch of water molecules in that beaker. All right. And so so if I'm going to predict a product, okay, I'm going to go ahead and quickly draw in the number of original hydrogens that I have before the reaction. So I have one there, I have none here, one here, and two here. So I won't go through the explanation. Hopefully you guys understand. And so if I'm going to look at this double bond, since there's no hydrogen on this carbon, then that means when the reaction does occur and that double bond is destroyed in the course of the reaction, that OH that I'm adding, I'll do this with green, the OH from the water molecule is going to attach itself onto the right side of that carbon where that double bond was there prior. And so this hydrogen is going to go to the side that has more hydrogens. And so I'm going to draw it like this. And so if you guys are looking at this structure, I have two hydrogens on the right hand side. And so if I have another water molecule and I'm trying to perform a hydration on this double bond, I'm going to take this hydrogen and connect it to the carbon that's on the right since it has more hydrogens. And last but not least, I'm going to go ahead and connect that OH to the carbon that has the least number of hydrogens. And so I'm going to go ahead and clean up my arrows. There's just a lot of movement that's going on. And I'm just going to go ahead and write my final answer. So remember, in the course of the chemical reaction, that double bond is gone and it's being replaced by OH and H, which is basically a water molecule. And so if I were to erase all of the hydrogens, because if you recall, my skeletal structure does not require for me to draw hydrogens on carbon, but it is required for heteroatoms. This would be my final answer. Okay. So hopefully you guys are understanding the pattern. So let's go ahead and do it again. Here we have a water molecule, and we have H2SO4 as our catalyst, so our solution is very acidic. We only have one double bond this time, and so I'm going to go ahead and draw in all of my hydrogens. So I have one hydrogen here. I have no hydrogens there, just because it already has 4 covalent bonds. And so if I were to take that water molecule, and if I were to separate it, then that hydrogen is going to go here at the bottom, and that OH is going to go at the very top. And so if I were to copy my structure, I would get an OH, and I would get an H. Okay. Now if I want to ignore all of these hydrogens because they're not really included in my skeletal structure, I can do so. If you want to keep them, that's fine. But this would be my final answer. All right, so last but not least, we're going to go ahead and do this last molecule. So once again, we're going to go ahead and react this. With water and H2SO4. So water is our second reactant. And H2SO4 is just our catalyst. It's just going to catalyze that reaction. And so once again, we're going to go ahead and draw all of my hydrogens. That's between the 2 carbons over here. That contains a double bond. I don't need to write the hydrogens that's outside of those double bonds, just because there's no reaction that's going to occur. So those hydrogens are present. And if you look at the carbon on the left-hand side, there's already 4 covalent bonds. So there's no hydrogens present. And so it looks like since the carbon on the right has more hydrogens, that's where this hydrogen is going to go. This OH is going to go to the side that has the least number of hydrogens. And if I were to draw the final structure, and I'll include both the hydrogens and the OH, then the OH is going to be here, and that hydrogen that we just added is going to go here. And if you want to demonstrate where the original hydrogens were, they're still in the same position. Okay. Now, if I wanted to represent this without any hydrogens, just because we don't depict hydrogens for skeletal structure, except for heteroatoms, this would be our final answer. All right, so that's pretty much it for this lecture video. Hopefully you guys understand how to predict the products of an addition reaction, whether it's hydration or hydrogenation. All right, so in the next lecture video, we're going to be talking about aromatic compounds, and that would be the final item that we're going to be discussing for chapter 11. See you guys in the next video.